Hi everyone, my name is Amit Swain. I am a researcher at TCS Research, and today I am going to present our work, an energy efficient and elastic edge cloud for computational sensing in smart geriatric homes. In the realm of edge computing, a new computing model has emerged which mimics cloud-like behavior but close to the edge. This is popularly known as edge cloud computing. Edge cloud computing offers privacy-preserving low-latency compute in the local network and has been incredibly popular because of its many advantages. The first generation of these edge clouds were on-premise micro data centers. Micro data centers were used in industry spaces, healthcare, and also in smart homes. But these are power hungry, inelastic, as well as occupy significant physical space. Because of this, low power single board computers are currently being investigated. They have several advantages and have evolved in terms of computing capability as well as reduced form factor. The clusters of these miniaturized boards could be a potential replacement for the micro data centers. In the present day, healthcare facilities are integrated with complex sensor networks to cater to their patient monitoring applications. In the figure on the right hand side, you can see a representative diagram of a healthcare building with sensor nodes spread out throughout the facility in every ward and in every floor of the facility. Now, all of these sensor nodes might not be active all the time. So there might be a few number of active sensor nodes and the rest of them idle. This generates a lot of sensor data which needs to be ingested at the edge layer or by a edge cloud. So the edge cloud and its component compute nodes or the worker nodes must be able to scale as per demand and should be able to allocate the sensor node tasks. So the current work investigates the feasibility of using low-cost SBC clusters in this particular context. It formulates an elasticity framework so that the current edge cloud will be able to scale as per the requirement. Yet another aspect while monitoring in ambient care homes and healthcare facilities is the physical context. For instance, the occupancy. As the data suggests, bed occupancy rate varies significantly over time, which indicates that sudden peak in BOR will put increased load on the edge infrastructure. We know that sensors measure information from the physical environment, and from this information we can derive the physical context. This happens in the sensor layer. In the edge layer, the system-driven aspects such that energy consumption, CPU usage, inference time, these are completely disjoint from the physical context in the sensor layer. So computational sensing has the capability to form the bridge between both these aspects and connect them. So using the inherent variability that exists in the physical context, like in this case the occupancy, we can selectively execute and use our computational resources so that we can reduce the burden on the edge infrastructure and simultaneously save energy. Now, with an interesting use case that is monitoring in a smart geriatric home, this paper proposes an elastic and energy efficient edge cloud that leverages the scalability of its low-cost slave cluster or the worker nodes with an elastic framework that can scale as per requirement. Also, a system architecture that is specifically tailored for computational sensing. The key contributions of this work are an exhaustive comparative study of the impact of computational approach versus the always-on inferencing approach on the energy consumption in the edge cloud, as well as estimating the monthly budget using an human occupancy data set as physical context. both for the micro data center approach as well as the proposed Elasticity Framework. Now, let us have a look at this detailed system architecture of our edge cloud platform. The figure on the left shows a block diagram of the edge cloud platform, and the figure on the right hand side shows the internal view of the real edge cloud platform. Now, starting from the sensor network, we can see there are several sensor nodes. A generic layout of a sensor node has been provided where it has a IoT module, signal conditioning circuit, sleep module, and several sensors. Now coming to the edge cloud platform, it has the host edge and the slave cluster. The communication between the sensor network and the host edge happens through a protocol known as MQTT. MQTT is a low latency PubSub based IoT messaging protocol. The MQTT client is installed in the IoT module, and the MQTT broker is there in our host edge. Also, there is an NTP server, which stands for Network Time Protocol, and it maintains time synchronization between the sensor node and the edge cloud. Time synchronization is key for time critical diagnostic aspects as well as for applications involving multi-sensor fusion. Then there's a task allocator which allocates sensor node tasks into topics and then maps them to the respective node in the slave cluster. The communication between the host edge and the slave cluster happens through an internal network switch. For the outgoing topics, there is a bidirectional flow that also happens to the same MQTT protocol. Here, the internal network switch has been labeled in the diagram on the right hand side, and the slave clusters have been shown. The task allocator in the edge cloud plays a key role, especially when the number of sensor nodes in the network is large. The task allocator assigns the node task and maps them to the specific workers in the slave cluster. So there are several algorithms to solve the assignment problems. In this case, we have used the Munkres algorithm. The Munkres algorithm can be shown as a linear optimization model given by the following expression, and it can be implemented both as a bipartite graph matching problem as well as in form of a adjacency matrix. On the right hand side, you can see a large unbalanced matrix. Munkres algorithm usually works for square matrices. So in this case, we have modified the Munkres algorithm into an extended Munkres algorithm which works also for the unbalanced matrices. First, the row sum and the column sum is calculated, and based on the column sum, the individual elements are sorted. And then the main matrix is split into square submatrices, and each of the submatrices is then used for applying the Munkres algorithm. Now, the node tasks are represented by N1, N2, and so on in the matrix, and the worker nodes are shown by M1, M2, M3, and so on. So in each of the submatrices, using the Munkres algorithm, the mapping of this node task to the respective worker node is done. The Elasticity Framework comprises of a modified cost function with certain constraints. Earlier, in the micro data center approach, all the active tasks were mapped to all the workers in the edge. So the value of M used to remain constant. Now, in this case, the value of M should change as per the number of active task groups. The figure on the right hand side shows a matrix, and it has some specific task groups T100, T200, referring to the number of tasks between 1 to 100 and number of tasks lying between 101 to 200 and so on. We can also see that there are some specific deadlines like 200, 350, 500 milliseconds, and some worker groups, 1W, 2W, and so on. So first, the number of available workers in a group are computed using a basic Moncrief algorithm, and then the extended Moncrief algorithm is run to map individual tasks to respective worker groups. We have formed a modified cost function, which is a product of three functions corresponding to the power consumption, CPU usage, and the inference time. The cost function for the power is shown as a dependent on the instantaneous power and the maximum power. The cost function for the CPU usage is again like there are some specific deadlines, there are some specific thresholds on the CPU usage for under usage and as well as for over usage of the CPU. And for the inference time, there are some specific deadlines. The figure on the right hand side on the top, it shows a sample run and there are some specific cost function values. We can take T200 for instance. So T200 in a micro data center approach would have given a cost function value of 37. And in this, using the elasticity framework, the allocation has been done with a value of 32, and it has been allocated to 2W worker group. The figure on the bottom shows a surface plot of the cost function for a specific value at PI equals to 3.5. And we can see that at specific points where the thresholds have been declared, so the cost function takes a higher value and thus preventing any allocation at that point. In order to evaluate our computational approach, we have taken a sample dataset, which is a radar-based action recognition dataset, and its corresponding ML model from a paper. The figure on the right shows a view of the machine learning model used. It takes input from a radar sensor, which is a panel radar sensor, and then the classifier consists of two-layer classifier. It's an ensembled classifier which has been trained with 24 features in layer 1, 45 features in layer 2, and a battery classifier model has been used. We can see the actions corresponding to A1, A2 to up to A7 has been described. What we have done is modified this ML architecture in a way that the layer 1 is used as a binary decision block to distinguish between movement and no movement, and then selectively execute the ensemble classifier to get the proper action recognition, but only in the case when movement is detected. If there is no movement, there is no need to execute the ensemble model. So can this approach help us to improve the system-driven parameters like energy consumption, CPU usage, etc.? Next, the evaluation is carried out in two stages. First, the small-scale evaluation. In the small-scale evaluation, the performance of the machine learning model was seen by varying the delay period. The delay here is the duration between two successive inference calls to the machine learning model. The power consumption for a single task has been shown in figure A, and the corresponding CPU usage in figure B. We can see that the ensemble classifier consumes more power and also has more CPU usage. Coming to the large scale evaluation, here the performance parameters were observed by scaling the number of tasks, keeping the delay fixed. So these are the charts for energy consumption, CPU usage, and inference time. We can see a difference between the layer 1 execution and the ensemble classifier. And this difference can be leveraged by using this computational approach. So when we use the computational approach, the times when no movement will be detected or there will be no occupancy, so we can actually save on the energy consumption. Next, we use an occupancy dataset to evaluate an energy budget over a month using our computational and elastic approach. Figure A shows the variation in occupancy with time, and for over a month, the energy consumption has been calculated using approach 1, the computational approach, and approach 2, the conventional approach. Then, taking 200 tasks into consideration, the energy consumption for elastic framework and the data center based approach has also been calculated. We can see that the data center approach definitely consumes more energy over a month. Firstly, the added advantage of using computational approach over the conventional approach was observed. It gave us around 100 watt hour extra savings, and then using the elastic approach over it, 12,000 watt hour savings, almost 15%, was produced while running 200 tasks as the task constraint. This also validates the result obtained by the following papers, that age-assisted control strategies can actually optimize system-driven aspects such as energy consumption, CPU usage, based on the insights that were learned from the sensor data. And it also stresses on the importance of using computational sensing for optimizing system parameters. And lastly, the idea of having an edge compute unit that mimics edge-like behavior in the local network and also has been tailored for computational sensing applications is of immense significance. Thank you. If you'd like to collaborate or you have any queries, please feel free to drop an email.